Hi guys, in this lecture we're gonna look at Bayes equation. So what is Bayes equation? Well, it's an equation for flipping conditional probabilities. I'll just write probs. So what does that mean? So let's say we know probability of B given A and want probability of A given B. That's an equation that lets us do that essentially. Now, up until now we've used a tree diagram, and in general you can still use a tree diagram to do this. It's just turning that tree diagram. So we're turning the tree diagram into a formula. So let's revisit how the tree diagram worked in the abstract. So we know probability of B given A, so our tree diagram would look like we first split into A and maybe A complement, and then from there it splits into B complement. Yeah, B complement. All right. Now the probabilities here are probability of A, and then probability of A complement, which is obviously just 1 minus probability of A. And then for the second stage, right, it's we have the probability of this branch is the conditional probability given A, what the probability of B is the probability of B complement given A, etc. All right, actually, no, I'll fill that in. All right, so this one is probability of B given A complement, and this one is probability of B complement given A complement. All right, so how would we calculate the probability of, we want probability of A given B? Well, we have our trusty, or sort of gold standard formula here, that this is the probability of A and B divided by the probability of B. Now, the probability of A and B is simply this path along the tree. So what that equals is the probability of A, which is the first path, times the probability of B given A. And that's the second path. All right. Now, to compute probability of B, right, we need to compute the probability that we need to sum all the different paths that land on a B. So this is this path that we've already done, and then there's this other path down here that lands on a B as well. And then we sum those together. So we have probability of A times the probability of B given A, which is the same as the numerator, plus now the other path, which is probability A complement times probability of B given A complement. So actually, and then this is probability of A given B. Right? So it's the probability of A given B, and then what we know is the probability of B given A and B given A complement. So this is flipping the probabilities, and this is just called Bayes' equation. So this is Bayes' equation. Alright, so why do we have a separate equation? We could just use a tree diagram. Well, in certain situations when there's a lot of possible paths, it's sort of easier not to have to draw the whole tree diagram to compute things. That said, the tree diagram sort of forces you to use the correct probabilities, and it's a nice way of keeping track of things. So if you want to use a tree diagram, you can. But a way of So in a situation where it might be handy is when you have more than two possibilities at first. So with multiple possibilities, with many. Initial possibilities. So suppose, let's say A1, A2, A3, and A4 are mutually exclusive and exhaustive possibilities. So anything, so are mutually exclusive, and exhaustive. These aren't, so what that means is that anything has to land in one of these, and it can only land in one, right? These partition the space into 4 possible things. So before, our mutually exclusive and exhaustive possibilities were A and A complement. Here, we're going to have 4. So our tree diagram would start to look a lot more complicated. We'd have A1, A2, A3, A4. And suppose for each of them we know probability of B given A1, probability of B given A2, etc. But we want probability of, say, A1 given B. Right. So how would we use this with, well, all right, so each of these then splits into B complement, B complement, B complement, B complement. Okay. So in this case, I think it might be easier if you're confident using it to just use Bayes equation. So how does that work? Well, we want probability A1 given B. This is the probability of A1 and B divided by probability of B. Okay, so now we break the numerator and the denominator down into the probabilities we have. So to get the probability of A1 and B, we first do A1 and then do B. So then the numerator, I guess I'll use green. The numerator becomes the product of probability A1 times the probability of B given A1. This is, of course, the same as if you were using the tree. And then for the denominator, probability of B, one way to think about Bayes' equation is that we're going to look at all the different ways B can happen and add them together. And it'd be the same if we were looking at the tree diagram, all the different ways B can happen. Except for we don't necessarily need to draw the tree diagram to get the correct formula. So, which is, sort of the point of Bayes' equation. Alright, so what is probability of B? Well, first we could have A1, and then we could have B, probability of B given A1, or we could have A2 and then B, so probability of A2 times probability of B given A2, or we could have probability A3 times the probability of B given A3. And the last sort of way to get to B is the probability would be to do A4, so probability A4, and then B, so times probability of B, times probability of B given A4. Okay. So putting that all together, what our answer is, well, it's simply the numerator divided by the denominator. And this is the long formula. If we wanted to, we could go through, make the tree diagram, and fill in all the probabilities. But essentially what Bayes' equation does is it just turns all that into the formula you'd get in the end anyway. And you don't have to label the lines on the tree diagram that you don't end up using to compute the probability you're interested in. Okay, that's been a lot of abstract stuff. So in the next part, we're going to look at some specific examples. All right. All right. Hi guys. Now let's move on to using Bayes' equation to compute some probabilities. All right. So this is the second part of worksheet 8. All right. I'll put my name on. I don't know why I feel like I need to do that. Whatever. Okay. So we're flipping conditional probabilities. Use Bayes' equation to compute the probability that a person who tests positive has the disease. So A is the event that a random person has sickle cell anemia, a complement that they don't. Let P be the event that a random person tests positive, and N the event that they test negative. Okay, so we want to compute the probability of having the disease, probability of A given a positive test. And so, right, by definition, this is probability of A and P divided by probability of P. And using Bayes' equation, which is essentially what falls out of the tree diagram, the probability of A and P we write as the probability of A times the probability of P given A. Now just one tip, how you know you're sort of on the right track, is that the conditional probability you get in the numerator, the probability P given A, should be the flipped of the one that you're trying to compute. We're trying to compute A given P, and what shows up in our equation is P given A. So that's good. All right, now on to the denominator. So it's the probability of P, so the probability of a positive test, and we want to just sort of enumerate all the ways that can happen. So you can have the disease and have a positive test, or you cannot have the disease and have a positive test. So we have the first way, let's say you have the anemia, probability of A, times then the probability of a positive test given A, plus the other way, which is that you don't have the disease, probability A complement, and you still test positive, probability of P given A complement. All right, so that's Bayes' equation. So now that all that's left to do is plug in the values given the data. Okay, so probability of A is the probability that you have the disease, so that's 1 in 1,000, so that's 0.1%, or probability of A equals 0.001. Fairly uncommon. All right, now we want the probability of P given A. So the probability of a positive test given that you have the anemia, that's the sensitivity by definition. So it's 99% right here. So we have, this is 0.99. And then the other probability, so probability of A complement is of course just equal to 0.999. And then probability of P given A complement, well, this is the probability of a positive test given that you don't have the disease. That's by definition the false positive rate, which is 1 minus the specificity. So 97% of people who don't have the disease test negative, so 3% of those who don't have the disease test positive. All right, so now we just plug these in. So this equals 0.001 times 0.99 divided by, again, 0.001 times 0.99. again, one thing that should always show up if you're doing things correctly is that the expression you have in the numerator should show up somewhere in the denominator. It shouldn't be the only term, but it'll show up somewhere, the exact same thing. So we have that in the numerator and the denominator. That's good. All right, now probability A complement, so that's probably you don't have the disease, so 0.999 times the probability of not having the disease and testing positive, which is 0.03, and this equals roughly, actually I'll put it over here, roughly 0.99, 0.032. So 3% of people who test positive actually have the disease. And the probability that a person who tests negative doesn't have the disease. Well, I've actually run out of room here. Well, let's see, I'll just be a little more compact maybe. So, and be a little faster, as it's basically the same computation. So if we want so that's the first part. If we want the probability of not having the disease, given that you test negative, well, by Bayes' equation, this is going to be probability of not having the disease, probability of not having the disease times the probability of testing negative given that you don't have the disease. Again, we have the flipped conditional probability to the one we're after. That's great. Now on the bottom, we know we're going to repeat this term. So we have probability not having the disease times the probability not having the disease given testing negative given that you don't have the disease, plus the other way you can test negative is if you do have the disease. So probability of A times the probability of testing negative given that you have the disease. All right? We plug the numbers in. So probability of A complement is 0.999 times the probability of testing negative if you have the disease. That is precisely the specificity, which is 97%. So 0.97, right? And we repeat that on the bottom, 0.999 times 0.97 plus the probability of having A, which is 0.001, times the probability of testing negative if you have A. Well, so it has a sensitivity of 99%, so that's the rate that you test positive if you have the disease. So the rate that you test negative is going to be 1%, so 0.01. All right, if you do that out, and I apologize for running out of space, that equals roughly 0.999989. That's really close to 1. So what this is saying is that given this test, if a randomly selected person tests negative, it's almost a certainty that they don't have the disease. But if they test positive, it's only about a 3% chance that they do have the disease, which is a lot higher than a random person having the disease without testing positive, but it's still not very high. Yeah, if you're interested in like medical testing, what this would be called the negative predictive power and the positive predictive power. So this would be, this is just an aside, you don't need to know this. So positive predictive power. And this is negative predictive power. So this test is very strong negative predictive power, not very strong positive predictive power. And that's really just a result of the fact that it's rare to begin with. So if a disease is rare, tests for it will have low positive predictive power. That's just how it works. All right, and obviously you can do exactly the same thing using a tree diagram. You should get the same answer. So that'll be just good practice for you on your own. All right, question 2. Suppose that now that you have a less common disease that affects 1 in 10,000 people, but you have the same screening test, what's the probability that they have it given that they test positive? All right, so I want you to do this one on your own. I'll upload solutions just to practice using Bayes' theorem, and you can follow the previous problem as a template. All right, so with these two problems, you had the sort of the simplest situation where you had two cases to deal with. They did have the disease or they didn't have the disease. So let's move on to something that's slightly more complicated, use of Bayes' theorem. So the tree diagram would be a little bit bigger. All right. So the partisan breakdown is roughly 40% Democrats, 32% Republicans. These just self-identified, people who self-identify in the survey, and 24% other. This is according to a survey I read. I don't really remember how necessarily accurate it was. All right, so now universal healthcare, also known as Medicare for All, is supported by 80% of Democrats, 51% of Republicans, and 65% of, people. P-O-P-L-E, sorry about that, who identified as other. Okay, so use Bayes' equation to compute the probability that a random person who does not support Medicare for All identifies as a Republican. Okay, well, so we'll have to name our events here. So let's say D is the event that a randomly selected person is a Democrat, or identifies as a Democrat. Yeah, whatever. R equals Republican, and let's say I for independent equals other in this case. It's others. In the actual survey, it was people identified as independent and just people who didn't want to answer the survey for whatever reason. Okay, and among those people, 65% of them support it. All right, so what we want is the probability of being a Republican, given that you don't support Medicare, universal health care. We have to assign symbols for that too. So let's say U equals supports universal health care. And then let's use a $sign for against. All right. So we want to say the probability that somebody is Republican given that they don't support healthcare. Well, by Bayes' equation, this is going to be the probability that they are a Republican times the probability that they don't support universal healthcare given that they're a Republican. Again, we have the conditional probability flipped, so that's good. And what do we divide by? We divide by all the different ways you can not support healthcare in this situation. So you could be a Republican, so probability of a Republican times probability of not supporting universal healthcare given that you're a Republican. Or you could be a Democrat, so the probability that the person's a Democrat times the probability that they don't support universal healthcare given that they're a Democrat, plus the probability that they're an independent, so this is the third option, times the probability that they don't support universal healthcare given that they're an independent. Okay, so now we just plug these numbers in, all these numbers we have. So the probability that somebody's a Republican is 32%, so this is 0.32 times, and so it turns out that, according to this survey anyway, 51% of Republicans support universal health care, so that would mean percentage 0.49 of them don't. And then, alright, so then we have the same situation below, 0.32 times 0.49 plus, alright, the probability of a Democrat is 0.44 times the probability that a Democrat doesn't support healthcare is that's going to be 0.13. plus the probability of being an independent, 0.24, times the probability that the independent doesn't support. So if 65% do, then I guess that'll be 35 don't? Yes, 0.35. Alright, and what does that come out to be? You plug that into a calculator, and you do need to be careful with these long expressions that you plug it into the calculator correctly. So this equals 0.52, roughly. Yeah. Which may be surprising. A random person this is saying that a random person who's against universal health care, they have even odds of being a Republican or not being a Republican. It's not like the only people who oppose this idea are Republicans. And yeah, also if you were to use this data to compute the percentage of the population that supports universal health care, so just compute probability of U, which you code with this data, you'd find it's about like 70% of the population, I think. Yeah, really popular idea, but somehow it's been phrased as this really partisan issue, and it actually is just not so partisan. Anyway, thought that was kind of interesting. Okay. Again, you can verify all this with a tree diagram. You should get exactly the same formula. All right, let's look at an even more complicated use of Bayes' equation. All right, so I guess when I say complicated, I just mean we're splitting it into now there's 5 different categories. So in the original examples, there were 2 categories really. Either you had the disease or you didn't have the disease. In the next example, there were 3 categories based on political affiliation: Democrat, Republican, other. And now we have 5 categories, which is these 5 different types of LEDs. All right, so we're going to use, so F is failure. So probability of F is the probability of failure. That's just the name of the event. All right, so what we want to compute is that if an LED fails, what is the probability that it was of type 4? So type 4 is this one. And they're the most numerous of any of the types, but they also have a low failure rate. So let's see how that plays out. So in this case, probability of failure, probability of being type 4 given failure. All right, so Bayes' equation says that this is going to be the probability of 4 times the probability of failure given 4. All right, so we have the flipped conditional probability. That's good. And then we divide by all the different ways. So all the different ways you can fail. So you could be a type 1 and fail. So being a type 1 and failing has probability 1 times probability of failure given 1 plus you could be type 2 and fail, probability of 2 times probability of failure given 2. Alright, and so on. So probability of being type 3 times probability of failing given that you're type 3 plus probability of 4 times probability of failure given that you're type 4. Alright, and this is our repeat of the numerator down in the bottom, which is good. That should always happen. Alright, and notice that in our conditional probabilities, in the numerator and the denominator, the order is flipped from the result we want. Here, failure is what is given, and then everywhere else we have a conditional probability. It's always the probability of failure given something else. So that's another just sort of rule of thumb that should be true as you're doing these problems. All right, so we just plug the numbers in, right? So probability of being 4 is 0.3. 0.3 times the probability of failure given 4 is 0.003. And all right, so now we just plug these numbers in. Probability of 1 is 0.15 times probability of failure, given that you're 1, is 0.01 plus probability of 2 is 0.25 times probability of failure of being 2 is 0.005 plus probability of being 3, which is 0.1 times the probability of failure if you're 3, which is 0.15, plus the probability of being 4, 0.3 times 0.003, the failure given that you're type 4. And lastly, oh my goodness, I forgot it over here, the probability of being type 5 times the probability of failure given that you're type 5. And that is, so probability of being type 5 is 0.2 times 0.004. Alright, so this is an example of a situation where you really wouldn't want to use a tree diagram. Well, I mean, you could. It would just be a really big-ass tree diagram, basically. It would take up a lot of space. I mean, the equation itself takes up a lot of space. Alright, so you plug this into a calculator. What do you get? It's roughly 0.15. So the last, wow, I can't write a 5. That is legible. The last problem, question 5, is of a similar nature. Except, yeah, there's just the situation is slightly different. Wow, I can't spell for anything. You're not given the exact percentage of each division. But the information you need is all there. But hopefully, with the previous examples as templates, this should be pretty doable. All right, that's all for now.